Hello friends, I welcome you all to this session on C++ programming and numerical methods, basically solving numerical methods in C++. So now in the previous lecture you have seen this method, that is Jacobi method of iteration, to solve or to model the system of linear equation. Now this is not a very beautiful method because it takes more number of iterations, and let me show this to you. So let's say I am creating one variable count and assigning 1 to it, and then what we'll do here is uh, after every step we have to increase the counter, and once the program finishes it should give me the number of counts, that is number of iterations in that particular program. So if I run it, so it took 20 iterations to arrive at this particular answer. And what will happen if I increase the precision from -5 to -8, let's say, then it will take 32 to get the exact answer 111. So just remember that it took 32 iterations for the convergence criteria of 10 to the power -8 to arrive at 111. How many iterations? 32 iterations. Now let us discuss this particular method, that is Gauss Seidel. So this method is called as Gauss Seidel, and in Gauss Seidel method what we do is, once we have the value of x1 known, then instead of waiting for the next iteration to use this particular evaluated x1, what we'll do is we will directly use this x1 here. That means this will be 1. Once this is also done, so you will be having now x2. So the x2 will be used in the same iteration as well as this x1. So what will happen? Due to this, the convergence rate increases. It becomes very fast. So previously in case of Jacobi, we took guesses. Okay, we will be taking guesses. But when it comes to x2, we will be using the same value which we have obtained right now. And once we know this x2, then we will be using the same value to in the next evaluation of next variable, that is x3. So that in the same iteration the evaluated x1 will be used every time as well as the evaluated x2. So this will increase the speed to the next level. So let us come to this program and let us just modify it slightly. So x1, okay. So in the first step you won't be having your x2 and x3. So we will be using guesses. In the next iteration, as x2 is known, so x1 is already evaluated here, so we will be using the same x1. And as x3 is not known till this point, so we will be using the guess value only. Then in x3, as both x1 and x2 have been evaluated, so we will be using them. And that's it. This is the only difference. If I run this program, previously the program took 32 iterations for this convergence. Now let us see how many iterations it will take for the same convergence criteria. So if I run it now, it took only 13 iterations. Look friend, only 13 iterations to arrive at the answer 111. So that is the reason why Gauss Seidel is much more preferred in comparison to Jacobi when it comes to solution of the system of linear equations. And if you are confused that where to write x1 guess, where to write x3, so you can do what? You can in fact remove guess from every equation. Every equation you remove guess. Okay, now there is no guesswork here. So what you will do is, you will initiate, though you have taken this, now you do what? You directly write, where I am writing, you directly write x1 same as x1 guess, then x2 same as x2 guess, then x3 same as x3 guess. So if you do this, then what will happen, that initially as x1, x2, x3 they are same as guess values, so you can use x1 here, x2, x3 in the same in the same iterative equation format, because here x2 is nothing but x2 is nothing but x2 guess, x3 is nothing but x3 guess. Once x2 is known, you are using the same x1 because x1 now will be updated. X3 is again x3 guess. Once x1, x2 both are known, they will be replaced here. So if you run it, you will be getting the same thing. So in this way, you can make the program much faster, very elegant. Okay. Now you must be wondering that, is this the only way, because there will be so many equations? No, this is not at all necessary to write like this. You needn't have to write every equation like this. I told you na in the Jacobi case that we can use arrays for them. So in the next lecture, what I'll do is I will try to solve this system of equation, or basically this differential equation, d2t by dx2, and that is equal to 0. This is a very simple and very used case when it comes to heat conduction for one dimensional cases, where this wall temperature is, let's say, T1 is, let's say, 100, and this wall temperature is, let's say, 30 degrees Celsius, and I am interested in finding out the variation of temperature in the wall. So this can be done very easily using Gauss Seidel. So how that is done, we will see it in the next lecture. So in this lecture, till this point only, thank you very much for watching it. Take care.